thousands. It has been a very fast-moving subject and very exciting subject, and I thought it would be nice to hear recent developments from somebody who is deeply involved in the matter, and in particular with the latest developments achieved through the James Webb telescope, which Luigi will talk to us about today. So, please.
Thank you so much, Joanna. Thank you for the kind invitation. Today, I would like to talk about the first result obtained with the James Webb Space Telescope concerning the atmosphere. But it's okay. Before this, I would like to introduce the field of exoplanet. Okay, in this diagram, you can see the number of planets that we detected in function of years. Especially, we started in 1995 to discover this exoplanet orbiting around a main star, and after that, the number of planets that we discovered gradually increased, especially after the Kepler mission. And today we know more than 5,000 exoplanets. And if we put this all these planets in this diagram, what you can see on the axis, the planet mass of the planets in unit of Earth masses versus the semi-major axis of their orbit in astronomical units, that means the separation of each planet from its parent star, we have this picture. So you can see, you can see also from this diagram that each column is colored in different way, and each color is linked with a different technique for detecting exoplanets. So you can detect exoplanet using different technique, and each different method can probe different regions this time. And there are some holes like this one, and especially this one, because it's very difficult to find a small planet very far from the parent star. But we are very good to find Jupiter planet, hot Jupiter, super Earth planet, and also Earth planet very close to the parent star. These are the types of planets that we detected. So we detected a lot of Neptune-like planets, gas giants, super Earths, and some rocky planets. And here you can see the most successful techniques for detecting exoplanets, especially the transit method and the radial velocity method. And I'd like to talk about these two methods because we don't have time to talk about all the other methods. So these are two clever indirect methods to find exoplanet. This one is the Doppler method or radial velocity method. Okay, you can take a picture of the star, or you can take a spectrum of the star, and the spectrum of the star. You see absorption line. From the position of the absorption line, you can measure the radial velocity of the star, so you can estimate if the star is approaching or is moving away from us. But if there is a planet orbiting around the star, you will see that the radial velocity, there will be a variation of the radial velocity of the star, a periodic variation. This periodic variation is connected to the orbital period of the planet. So you will see a periodic variation of the radial velocity of the star. And from the amplitude of this variation, you can measure specific. Okay. You can measure the planet, the mass of the planet. up to a factor scenario, where I is the orbital inclination of the planet, you do know the orbital inclination. And with this technique, the first exoplanet orbiting around main star was found by these two Swiss guys. It was Jupiter Mars planet, and these two guys won the Nobel Prize in Physics 2019, and you know how it started for a strong to win a Nobel Prize in Physics. Transit. In this animation, you see eclipsing binary system. So if you take the light curves of this system, you will see that the light is decreasing and increasing periodically. So you see primary eclipse and secondary eclipse. And the same phenomenon works for transiting planets. So if you see a planet transiting in front of this star, we will measure a light curve like this one. And the depth of the transit is related to the relation between the radius of the planet and the radius of the star. And this phenomenon is very similar to what we observed several years ago when there were the transit of Venus in front of the disk of our sun. So from if you observe a transit, you can measure easily the transit depth. So you can have a measure of the radius of the planet. You can measure the duration of the transit, so you can measure the velocity of the planet. So the semi-major axis of the orbit, the direction from this parent star. And here are some numbers. So if a Jupiter is transiting in front of a star like the sun, you will see a transit depth roughly 1% of the total luminosity of the star. But if it's a Earth-like planet orbiting, is transiting in front of the solar-like star, the transit depth is very small. So it's very difficult to find a small planet. And it's much easier to detect planet very close to the parent star, because you don't have to wait for one transiting. So why transiting planets are so important? Because if you detect a planet with the radial velocity method, you don't know if the planet is transiting. Probably not, because in order to have a transit, the orbital inclination should be very close to 90 degrees. But if you detect the transiting planet, you know that the orbital inclination is 90 degrees, and you can always measure the mass of the planet with the radial velocity technique, unless the star is very faint. And so if you can measure the radius of the planet, the mass of the planet, you measure the density of the planet, so you have an idea of what kind of planet you are observing. And so if you detect a transit planet, you can measure all the physical properties of the planet, or the orbital parameters, planetary system. And so you can very really characterize the planet and the planetary system. This is why there was a big effort to find the exoplanet, the transiting exoplanet, starting around 2000, with a lot of surveys, ground-based surveys. These are the most successful surveys, and 3 space surveys for all Kepler, and now this is still ongoing survey with TESS. So with ground-based telescope, you can have a light group like this one, and after that you have this signal, you can use a larger telescope to get a better measurement of the transit, because you need very accurate light groups in order to estimate the parameter of the transit, especially if you use the focus techniques that we pioneered many years ago. And this is another example of a lovely transit lighthouse that I obtained with the Cassini telescope, Loiano. And I take the opportunity to thank the Conservatory of Bologna for the time that I received in the last years for my program and for supporting other programs in which I'm involved. Usually I receive 1-2 weeks per semester, and in the last 10 years we published more than 20 papers with this data. And here is a picture of me with some students of mine, and together with Ivan Bruni, and this is the technician, one of the technicians, together with Roberto Galandi, at the Loiano station. So I also thank them for all the support during the observation. So coming back to transiting planet, now, as I told you before, if the planet is small, it's very hard to detect a transit planet. Well, it depends from the radius of the parent star. For instance, if we take 2 super-Earth planets like this one, GJ1214 and Corot 7b, these 2 planets are super-Earth planets, but GJ1214b is transiting in front of M star, while Corot 7 is transiting in front of G star. So the transit of GJ1214 is deeper than Corot 7b. That means that you can use a small glass ground-based telescope to observe this transit, but you need a space telescope to catch this transit. And so if you want to observe, to detect Earth-like planet transiting in front of a star similar to the Sun, you have to go to space. This is why Kepler's mission was done, and you can see here a typical Kepler light. Please pay attention to the epsilon axis. And you can see the precision of Kepler is 1 part in 10,000. So you can detect a very small planet with a very small precision. This was the situation before Kepler. This is a diagram where you see the radius of the planet relative to the radius of the Earth, function of the orbital period. And this was the situation after Kepler. So with Kepler, we discovered more than 2,700 planets, and there are still other 2,000 candidates that we didn't confirm. And also in the second mission, Kepler, we detected other more than 500 planets, and there are still another 1,000 candidates. And also we detected a lot of super-Earths. So super-Earths are planets with a radius between the Earth, the radius of the Earth and the radius of Neptune. And we don't have these planets in our solar system. This tells us that our solar system is rare in comparison with the other planetary systems that we found. And today we have the TESS mission, still ongoing, and these are all the candidates found by TESS. This was at the end of 2021. After the extended, the first extended mission, now we are the second extended mission. There are more than 6,000 candidates. We confirmed just 200, roughly 300 planets. So there is a lot of work to do in order to confirm all the TESS candidates. Okay, now you can measure the transit of the planet, but you can measure also the rotation of the planet. So you can wait that the planet moves and go behind the star, and you can see how the light would see changing. You can measure the brightness phase curve, so you can measure the brightness distribution on the planet during its orbital motion. So when the planet is moving from the night side to the day side, you will see this increasing of the flux coming from, this is the combined flux from the planet and the star, and then you will see the rotation. So, please.
The TESS and the Kepler are based both on transit, right?
Yes.
Yes. And the selection of the stars as the targets is needs any specific selection, or you can do randomly?
Well, the strategy, the observational strategy was different. These two experiments. For Kepler, they decided to observe just one field. For the idea was to observe the field for 5 years. They were able to observe for 4 years, and the idea was to find planet, transiting planet, which with large separation from the parent star, because in order to find a planet with a large orbital period, you have to observe for years. You have to observe one transit, and then if you observe just one transit, you cannot say anything about it. You have to observe at least 3 transits. So you need to observe the same star for years and years. Instead, TESS is doing all sky science. So it's observing sector of the sky, and stay in each sector for roughly 20 days. Then it moves. And now he completed.
Sort of wide field.
Yeah, very wide field, 24 degrees, huge field of view. And well, if you want to have animation with all the stars observed by TESS, which is very nice. Maybe I can show you later. Because this seminar is more focused on the James Webb Space Telescope. So, okay, so you can measure this phase curve like this one. This was observed with the Space Telescope. This planet is HD with this telephone number 1897333B. So you can observe the transit, the rotation, the phase curve, how the brightness of the planet change, and you can also measure what we call it the emission spectrum of the planet. So you can measure the light, the flux of the star when there is the occultation and before the occultation, and so you can measure the flux as a function of the wavelength, if you take the spectrum of the star. Or you can measure the transmission spectrum of the star. So you use the light of the star for probing the atmosphere. I have animation here. You see, if you observe the transit at different wavelength, you can measure different transit depth, because some light is absorbed by atoms and molecules in the atmosphere of the planet. So you can observe a transit at different wavelength. You can measure different transit depth, and then you can have a different measure of the radius, and you obtain the transmission spectrum of the planet. And so you can study the presence of elements like oxygen, carbon, sodium, potassium in the optical, or in the near or the mid-infrared. You can detect the presence of water, methane, and so on. For instance, if you use a ground-based telescope, you can use a long slit to put your target in a reference star in the slit, or you can use a multi-spectrum instrument, so you can obtain a spectrum for your target for reference stars, and then you can sum all the flux over the wavelength. You can obtain what we call this white time series, or you can divide your spectrum in beams, and then you can sum the flux in each beam, and you can obtain this time spectrophotometric time series for each beam. Okay, and then you fit each light curve, and so you can measure the transit depth for each light curve, and then you can have a measurement of how the planet, the radius of the planet changes as a function of the wavelength. So you obtain the transmission spectrum. And then you use models, theoretical models, to fit the data. And you can see what is the best model for fitting the data. And so you can have different models using different composition of the atmosphere. So in this case, this is a super-Earth GJ1214b. It's very hard to discriminate the composition of the atmosphere of the planet, but if you study a giant planet like this one, WST-B, you can see a lot of features like the presence of AIDS due to the right light scattering. You see absorption of sodium. You see presence of strong absorber, the optical, like the oxide, the titanium oxide, and then you can see a very nice feature due to the presence of water vapor here. And these are spectra obtained with the Hubble Space Telescope of different giant planets, and you can see that for a lot of them you can see the presence of water and other elements. This again are spectra, transmission spectra of rocky planet. So if the planet is very small, it's very hard to have an idea of the composition of the atmosphere of the planet. So this is what we can obtain with the instrument before the James Webb Space Telescope. And okay, this you can also measure the occultation, so you can measure the depth of the occultation. You can use the Spitzer to do this. You can have this nice light curves, and you can measure so the flux of the planet because you can measure the difference between the flux before the occultation and during the occultation. And this can be done with the Spitzer very easily, very hard to do in the optical. You have to go to the near infrared. And so that's something that you can do also with the James Webb Space Telescope. For instance, these are Spitzer observation of the occultation, this HD 189733b. And then again, if you measure the planet flux relation, you can have the emission spectrum of the planet. And then you can compare your data with models. So for instance, here there are two models, and then you can have information about how the absorbed energy is distributed over the entire planet. And also with the Hubble Space Telescope, it's possible to observe the emission spectra of several giant planets, like this was 43 billion. Here you can see Hubble Space Telescope and just 2 points from the Spitzer, so it's very hard to study this region. Now, James Webb Space Telescope, you can find a lot of very nice pictures on this website. You see how big is this instrument. Is actually the most powerful, the most ambitious and expensive telescope never built by a human being. You can see that the cost is larger than $10 billion, so large amount of money for a telescope. It's working fine now. Is the second Lagrange point. So far, so good. This is a comparison of the primary mirror of the Webb Space Telescope, the Hubble Spitzer. This is the electromagnetic window covered by the Webb Telescope, compared to Hubble Spitzer again. You can see that now we can study a window that before we couldn't. And there are 4 instruments on the James Webb Space Telescope: NIRSPEC, NIRIS, NIRCam, NIRI. All the 4 instruments are able to perform spectroscopy, some of them also photometry and coronagraphy. And 3 instruments work in the near infrared, and 1 instrument is working mid infrared. These are pictures of the instrument. This is the field of view of each for the instrument. The size here is 1 arc-minute, so very small field of view. These are how the star appear in each field of view. And the size. Okay, so there are 4 main pillars for scientific targets for the Webb Space Telescope. Study the early universe, study galaxy, the life cycle of stars, and the atmosphere of exoplanet. So the idea is to use this telescope for studying the atmosphere of the planet, so observing transmission, emission, spectra, and studying the population of the phase. I'm part of the Transiting Exoplanet Community Early Release Science Program. This program was accepted with this number. It's a very large collaboration, more than 100 people here. And the idea also is to study the performance of each instrument, to try to understand the systematics, the problems each instrument. And so at the end, to demonstrate the abilities, the capabilities of the James Webb Space Telescope in doing science. And the idea was to observe just a few targets and giant planets, because we want to test the abilities of the quality of the data, and analyze the data in a very fast way. So since the James Webb Space Telescope will be in space for a limited number of years, so it's better to understand as soon as possible the problems or the systematic of the instrument, in order that then you can produce science in a very fast way. So this was the aim of this program. So the program is divided in 3 sub-programs. Study of transmission spectrum using 3 different instruments, and one of the instruments is used in 2 different modes. Then the emission spectrum using IRIS, and then the phase modulation for what's for the 3D. And the first 2 parts were done. So we obtained the data, we analyzed the data, we submitted the paper. The paper has been accepted for these 2 programs. But for the last part of our program, the analysis is still ongoing, because the data arrived relatively late during cycle 1. So first part is about the transmission spectrum using different instruments, different configuration. The target selected was 39B that we studied very well the last years, is a hot giant planet with a mass similar to Saturn, but with a radius larger than Jupiter. That means that we expect extended atmosphere, like flooded giant planet, push-through giant planet. WASP-39b is orbiting around G8 main sequence star with elemental abundance very similar to the Sun. Why this target? First of all, because for time constraint, also the good target for observing it several times. You expect high signal to noise ratio. The parent star is inactive, so it's a quiet star, and also because we already observed this planet, the transmission spectrum of this planet with a very large telescope, Hubble Space Telescope, and with SPITZA. So we already know that there are fusion, and so it's also good for compare all data with the new data, James Webb Space Telescope. So NIRSpec, we used NIRSpec in two combination, clear and using this dispersed filter combination. So we observe one transit in the full wavelength of the instrument, and the second transit we observed in this range between 2.8 and 5 micron. NIRSpec has two detectors. We observed one transit at the end of July last year, and we observed with this configuration, so between 2.8 and 5. Why this? Because we want to explore this region and see if we are able to detect carbon dioxide. So this is what we expect to find. This is the white light curves. So we observed for 8 hours. We obtained more than 460 integration. And we observed a tilt element. You can see that there is a jump here. This is due to a change in position of a mirror segment. We don't know why happened, but it's not.
Meteorite.
But it's not a big issue, because then we can just move this point at the same level, so not a big issue. Exactly. So here you can see how the flux is changing as a function of time. The time here is now, this year. This is the light curve precision, the transit depth precision, so very nice precision for our data. And this is the transmission spectrum of the planet. And you can see a lot of points here and color a different way, because we used different pipeline for the data reduction, for the utilization of the data, for the data analysis. And each pipeline was developed in a dependent way. So we are very sure that our data are very robust, because all the pipelines are very consistent with each other. Okay, so this is why also why we are a lot of people. We developed a lot of software for analyzing the data. And yeah, we detected carbon dioxide very nicely. You can see here this feature. We detected water as expected, and we also there is here a little bump here, and this was explained later as identified as sulfur dioxide. So this is something that is produced by photochemistry. That means that it's due to the irradiation coming from the sun. So a chemical reaction due to the starlight. And this is the first time that we observe something like this. So this was expected, but this was not expected. So it's a surprise. Okay, again, we used the near spec in the this mode, so you observe the low resolution mode, but the entire wavelength region of the spec of the instrument, and we recorded for the 21,000 of the integration. So very nicely white light with a lot of points. And then you can pin your spectrum and obtain all these light groups. Again, you obtain the transmission spectrum, and again you can see many points colored in different way, and each color is linked to a different pipeline that we use. And you can see also the Hubble space data, space telescope data here, and the Spitzer data. So this is low resolution spectrum, but this is the best spectrum, transmission spectrum that I ever see. And we nicely detected water, of course, but it's very nice absorption due to carbon dioxide. And we also detected the sodium and carbon dioxide. Then NIRIS. Use NIRIS in this mode, in SOSS mode, single object slitless spectroscopy, covering this wavelength range from 0.6 to 2.8. Actually, NIRIS has one detector, single detector. The data covers this wavelength range view across two spectral order on the same detector. So on the detector, you see this fissure. The first order contains spectral range between 0.8 to 2.8, and the order 2 contains the spectral range from 0.6 to 1. Different resolving power. So these are the two orders. So again, we divide the spectral beams, and you have for each beam time series spectrum. This one fit the data, and you obtain the transmission spectrum. Again, the points are colored in a different way according to the pipeline. Here are the Hubble Space Telescope, and you can see that there is a good agreement between our data and the Hubble Space Telescope. And this is the comparison of our points with theoretical models. And so the back line is the base model, and there are other lines. Each color line removes a key constituent of our model. So if you can see that if we remove water and clouds, the spectra change in a very strong way. So we are sure that there is the presence of water and clouds in the atmosphere of the planet. Jump this one. The NIRCam. With NIRCam has a dichroic, so it's possible to obtain simultaneously time series imaging, also time series spectroscopy. This dichroic split the light in two channels: the short wavelength channel and long wavelength channel. The short wavelength channel, you can do photometry, so you can have an hexagonal pattern like this one, and in the long wavelength channel, you can have the spectrum star. We use this filter for the long wavelength channel, this prism, for covering this wavelength region, very large window. And for the imaging, use this filter, 2.2, between 2 and 2.2 wavelengths. micron. So we observed again was 39B, other 8 hours, and this is how the flux of the light change as a function of time. So this is the white light, this is the model, this is residuals, and this is the transmission spectrum. Again, using different pipelines. This is the Spitzer point. You can see the precision now that we have for studying the atmosphere of the planet. And this is theoretical models. Again, we found water very nicely. The idea was also to find the methane, but we can just add an upper limit of the abundance of methane. So we observed was 39 with 3 different instruments. One instrument was observed 2 different configurations. We obtained a very nice transmission spectra, and then we observed was 18B in order to measure the occultation. So the idea is to obtain the emission spectrum of this giant planet. This is this planet is hotter than the previous one. It's very massive, 10 Jupiter masses, and has a very the radius of the planet is a little bit larger than the radius of Jupiter. The source is very bright. It's a F6 star, and you use again IRIS to observe this rotation using again the single object slitless spectroscopy mode. You observe this was 18B for more than 6 hours. You obtained more than 2,700 integration, and so you obtained this is the white light hoods. These are example of other light hoods obtained at the different beams. Center this wavelength wavelength, and this you can see also the phase variation are nice. And then you for each the beam you can obtain the emission spectrum, so the flux of the planet, the ratio between the particles of the planet and stars, function of the wavelength. The red points are the points obtained with the Hubble Space Telescope. This 2 gray points obtained by Spitzer, this one by TESS. And so there's again a good agreement between the James Webb Space Telescope and the Hubble Space Telescope. And then it's also possible to obtain the planetary thermal emission of the planet. And so you can fit the best black body spectrum for your data very nicely. And then you can also estimate the brightness temperature spectrum. This is very important, because then you can easily see the future due to the various species in the atmosphere of the planet. So we observed that the 3 emission future due to the water, 1.4, 1.9, and 2.5, very nicely. And also we observed that this the downward slope of the spectrum, of the spectrum, due to the decreasing of this strong absorber in the blue part of the spectrum, due to titanium oxide and other absorbers. So that's also very nice. And at the end, this is the full orbit phase curve of was 43B. It's another hot Jupiter. And the data very nice. The analysis is still ongoing, so I can show you just this the raw data, the raw light curve, sorry. And what we can see from this light curves, you will see an initial downward ramp. It's strange. Also, there is a linear downward linear trend. You can see. So this is something that can, and it's like that there are no other systematics. So very, very. Okay, I'm at the end of my presentation. So the summary is that we observe the transmission spectra of this giant planet was 39 big. 3 instruments of the Webb Space Telescope. With NIRIS, we found potassium, water, carbon dioxide. With the NIRCam, we found water. NIRSPEC, we found again water, but also this sulfur dioxide of this time, carbon dioxide of this time, carbon monoxide. And also we obtain a low resolution spectrum with the NIRSPEC. And so very, very nice issue spectrum. So we spot these 2 molecules for the first time. Very important is sulfur dioxide. It's very important because it's something that is produced by photochemistry, as I told you. And also we observed the emission spectrum of P and this emission spectrum for again water and fissures and other fissures. Okay, and here, and I would like to tell you that we are organizing a school on high science. The focus of this 4th edition of the school is on the astrophysics, transiting exoplanet. The school will be held in Via sul Mare, close to Salerno. And the topics are this one, so statistics, transiting exoplanet, the determination of the parameters of the transiting planet, but also they will lecture about the atmosphere. If some of your students is interested to know something about this very exciting field, they are welcome. So thank you so much for your attention, and I thank you.
Thank you. Thank you, Luigi. Is there any question from here? Yes.
About the 2 observation with James Webb, atmosphere for these 2 odd gas giant planets, how they compare with respect to Jupiter and Saturn in our solar system in terms of properties about this?
Yeah, well, you see, they are different kind of planets because these planets are hot. These planets are very close to their stars. That means they are very hot. They close the orbit in a few days. Okay, so they receive a lot of radiation from the parent star. So very hot planet, and they are also different from Jupiter. This WASP 39 has a mass similar to Saturn, but a radius large to Jupiter. It's a giant planet. However, what we expected is something that we found in Jupiter: sodium, potassium, water vapor. So all the theoretical models are built on what we observed in the planet. So their atmosphere are similar, but of course the physical parameters are different. But also the amount of each species is different.
Other questions?
I'm just curious about the drop in flux that you had in
Yeah, here.
not this one,
This one.
no, the previous one. It was in NIRSPEC, I guess.
This one.
No, in the transit where we were mentioning the micrometeorite or something.
Mirror glitch.
The mirror.
Yeah.
The mirror.
Okay. Yeah.
But just curious if this is the only case where it has been seen in some James Webb observations,
I don't know. I don't know.
or how common, or let's say,
Well,
worrisome.
however, you have to consider that for this observation, we need a very long time series. So this is a different observation strategy. I guess if you observe a single object, you would need to observe for 8 hours. At least it's many different objects. Yeah, but yeah, maybe in this case.
That was very
Yeah.
expensive.
Yeah, this could be a problem.
Almost in the middle of the middle.
Yeah, strange.
Yeah, it's very
Not clear.
but it's
Is there any other question here or online? I don't see any comment or questions here, so we thank again Luigi Mancini for this nice talk. Thank you very much.
good.